Let's continue from our previous lectures, which was Drude model, the inherent flaw in it. It overestimates the value of heat capacity and underestimates the value of thermal velocity. Now, why this shortcoming coming from? The main reason that comes from this is that we consider uh, electron in a metal, electron in metals as a classical particle. Mm, not as a quantum mechanical. What's special about particle and quantum mechanical particle is that in classical theory or classical particle, we usually assume that all particles are identical and distinguishable. What we mean by that they are identical? It means uh, that they are same in every respect. Of course, they are all electrons. Of course, they will be same in every respect. And the second thing we assume that they are distinguishable means we can identify each and every electron where they are going, where it is placed. Although all electrons are there, but still we are able to distinguish. What does that mean is, suppose this is electron 1. Hypothetically, I mentioned this is electron 2. They are coming, they are going, and suddenly they collide at this position, and this go to in the direction, electron 1, electron go to these two directions. So we know that the moment they met and where they go. So we exactly know where they are going. So basically, in this way, we are distinguishable. But if there is a condition, electron 1 and electron 2, they're coming, and somewhere when they reach here, we do not know whether this electron is this electron and this electron is this electron, and they goes up. Now we do not know whether this is one or second electron, or this is one or second electron. So this is become indistinguishable, and they are distinguishable because we are able to identify each and every electron, and also like if there are two energy states, let's say E1 energy level and E2, one is sitting on this one and one is sitting on this position. Now these come on to electron from energy E2 comes and reach to the energy level E1, and electron from energy E1 goes to E2, right? So since we are able to identify where each and every electron, so this is considered to be a new state. Like earlier, when this electron was here and this one was here and second was here, so this is one state. Now second went on this place and one came on to this place. This is new state. But in quantum mechanics, if there is exchange, since they are identical, we are considered as in no new state, right? And also depending upon this behavior, they follow different statistics for energy distribution. Like classical particle follow Maxwell-Boltzmann distribution, and quantum mechanical particle follow Fermi-Dirac distribution. Because electron are basically in this is considered fermion. right? So what the Sommerfeld did, Sommerfeld introduced, consider electron as a quantum mechanical particle, not as a classical particle, which has led to the improvement in the theory uh, originally made by Drude. And by the way, Sommerfeld was a very renowned scientist in a way that I think he is the only scientist who four doctoral students actually got Nobel Prize and three postdoctoral students got three Nobel Prize. So overall, he has actually guided seven Nobel laureate in his career. Okay, now let's move ahead. Now, now first, before going this further, I will first discuss a little bit about this Boltzmann distribution and Fermi-Dirac statistical distribution. These are important because this will help in the other lecture as well. So first, Maxwell Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution gives the distribution of electron at different energy level, like where they are going to occupy, how they are going to distribute. So these are usually plotted, or they are usually described as Ni equal to N upon P e to the power minus Pi by AB. So where E is the Ni is the number of electron at energy level Pi. P is partition function. You will define as you will describe as function. And Kb is also Boltzmann constant. N is total number of electrons. Now what happened? And also this also can be written as in terms of probability. Probability of finding an electron at energy P is P naught Pi by Kb. Right. Now let's plot this. What actually uh, how the distribution look like for Boltzmann distribution. Suppose this axis is the energy and this axis is the number of electrons. Right, number of electrons. What does it say? As the energy is less, there are more and more number of electrons. Basically, it means that lower energy electron will first have to occupy the lower energy electron, and they are more populated as the energy goes, because it is minus exponential. As the energy goes high, there will be less and less electrons present there. So they are like this. And typically temperature T1, right? And at the temperature T2, it will look like the temperature. this energy level has more number of electrons, while higher energy level has less electron. And another important thing about this distribution is that n number of electrons can occupy the same energy. This is different from the quantum mechanical statistical distribution that we will discuss later. But here it means that two electrons can occupy the same energy level. So what does that mean? Like for example, we are heating. We are providing its energy. So electron will get energy and it will go to energy level X. Then another electron will be there and it will also go energy level X. Right? So it will absorb. Now all electron will go to energy level X. Then we again providing it. Then will go X plus 1. So basically, it to rise to give rise to a certain temperature, we have to provide more heat. So you see the relation why in our previous case when we mentioned that specific heat at constant value was overestimated. This is because by default our assumption was that it's a classical particle which follows Maxwell-Boltzmann distribution, and Maxwell-Boltzmann distributions can have two electron can have same energy. So when we excite, provide them energy, so all electron try to absorb energy and they actually absorb. So in terms, it is predicted that it will have high specific heat, but actually it is not the case. Right? Now the second distribution where we assume was for quantum mechanics was Fermi-Dirac sequence, where it is defined as f of t 1 upon 1 plus e t. Where f is the probability of finding an electron at energy E, at energy state E. There is a state with energy E, what's the probability that it will be occupied by electron? It is described as Ti upon 1 plus Ex, Ei minus Ef by kT. Now let's see how it's distributed. And they are follows, they are continuous, they follow, it is important, Pauli exclusion principle, which say that no two electron can have same quantum number. It means that no two electron can have a all at same energy state at the same state. There has to be some difference. This is the fundamental difference between the uh, previous Boltzmann Maxwell-Boltzmann distribution. Now here it's energy which is defined as EF, which is important in semiconductor process is or in metal. It's very fundamental energy that it will come again and again. Right now let's plot it. Now let's see how it will behave. Let's say at t equal to 0. Right? Now what we want to do, we want to plot the difference between f of t, probability of occupancy of energy E, and energy. Now let's say at t equal to 0 Kelvin, how it will behave. So what will happen? E Ei minus Ef kVt. where if we put 0, right? Now we have to find what it will happen. Now for if this energy EI is less than EF, so what will happen? This term will be negative, and that to minus. It will be minus infinity, which will be 0. So Fe will be 1 upon 1 plus 0 equal to 1. So it means that. So until energy is EF or at if its value is 1. Now if for EI is greater than EF, what it will happen? EI, when we put EI equal to EF, so this will happen, it will be exponential and infinity. So it will be very large. So it will be 1 upon 1 plus infinity. It will be 0. So basically it goes, it will be 0. So which means at t equal to 0, at t equal to 0, the all the energy, all the state below energy EF are occupied, and move for the energy more than EF, they are empty. There is no probability of finding electron there. So although there could be a state, but electron will not be there. So this is how we define a Fermi energy. Fermi energy at T equal to 0 Kelvin, where the until when all the electron are, all the state or all the energy are filled, can be occupied by electrons. It's the maximum energy beyond which the electron, finding the electron at that particular energy, if the states are there, is negligible. So this is when t equal to 0. Now let's say uh, at t equal to t1 some constant value. Now let's see how it should be here. So what it will happen? So first of all, when EF equal to L, when it, right? So what will happen? The it will be 1 upon 1 plus 1. So basically, irrespective of the value of whether it is T1, T2, or T3, the at E equal to F, the probability of finding a particle will be half. It's basically half this value, right? Now, for a given T1, if EI is smaller than EF, so basically it will be 1 upon 1 plus exponential. It will be something negative value, right? So it means and as when it goes very and very low value of if EI is very small than EF, it will be like 0. So it will be 1 upon 1 equal 1. But as E equal to very close to EF, so they will start like behaving like this. So this E equal to T1. Similarly, if we have another equal to equal to T2. So they will be same, but it will. I will explain its physical significance. Now, what's happening when we increasing the temperature? When we are increasing temperature, so the electrons that are there now they gain energy and they go for higher energy. Now, important thing is remember is that it follow Pauli exclusion principle. So no two electron can have same state. What does that mean? If let's say some electron has some energy like this one, right? And we provide only this much energy, only this, only this much energy, and right on x-axis. So what will happen? So all the electron that are there, it will see this much energy. It should able to go to reach this place, but this has already an electron, right? So this basically means that this electron will not be able to contribute anything because they cannot. One single energy cannot have two electrons, so they will not contribute anything. So eventually, there are less number of electrons that are available for to absorb more heat at a given temperature. So that's why it has a less specific heat. So mainly the electron which are closer to the Fermi energy and they only actually contribute. When we provide the energy, so only these electron will actually go and participate in the in energy gain, right? And these electron they are actually very small fraction as compared to the millions of electrons that are present, right? So while in the case of Maxwell-Boltzmann statistic, uh, there are large number of electron and all electron are able to absorb energy. So that's why it overestimate the specific heat. But here there are very less number of electron are available, and since they follow Pauli exclusion principle, they cannot two electron cannot have the same energy. So not although they should absorb, but they will not absorb because they will reach a place where there is no uh, place for them to sit. So they will not absorb. Eventually, there are a very small number of electrons that are available for absorb energy. This has led to the relatively less contribution of electron in heat specific capacity of the electron. Right. This is one portion, and the second thing earlier we have a very cube, right? And it has lots of electrons. They are electron ionic core everywhere, right? And we okay the electron everywhere. We assume that there is no interaction between this electron and core. But this is a positive charge and this is a negative charge. They are bound to be an interaction. So let's consider what will happen. Now first consider only the very basic only one. This is ionic core, this is positive, right? Let's plot a potential energy. Let's say this is position. Now, if this is an ionic core, it has positive charge, and there is an electron. Electron is at infinite, very far, very far. So it do not see any interaction. It doesn't come under the influence. But this case, very far, its energy will be zero, right? And let's say this is now as it goes, has come more and more closer to the ionic core, it has started to get intense, so its potential energy start to decrease. When it is very close, it goes down. It's very, very, very large value. Similarly, when it start to go away in this direction, it will start to increase, and when it is very far, it's goes to zero. Right? Suppose we have ion, and there are electrons are there, right? They are all bound electrons. They have very high potential energy. These these are bound electron, and there are these electron also they are free, but they are nearly free, not free. Free electron are those they are like outside this solid. They do not have any influence. These electrons are there. It has some influence in between them. So they are somewhere here. This somewhere here. They are under the influence of something, right? And those electrons which are bound, uh, they have very high potential energy. Now let's suppose these are four, only 4 point I'm considering. This is the four ions, right? Let's connect them together. Right? And let's also talk its Y position. Mm, Now, if we start the plot this kind of potential curve for all these values, all this position of ion in the lattice, which are peak position. There will be something like this. Then when there is the at position, the potential is very deep. So we can approximate or we can write these. So we can approximate this as a square wave. This is square. Okay. Now let's proceed further and see what the effect of this potential wall on the electronic behavior. Right now, before going to this, let me just briefly introduce you to the Schrodinger wave equation. Let's discuss Schrodinger wave equation. Which is defined as minus square by 2 d square where h is Planck constant and h bar is defined as 0.25 and 5 is 5 is wave function. It basically describes the probability of finding a particle, and Vx is potential energy. And is total energy. Now, first, just for an example, let's say this is a wall, right? And at one end, there is a string, and you have it is attached, it is fixed, and while the other end is free, it can be anywhere, right? Like one end is fixed, one is free, so it can have any possible wavelength or position, right? With the fixed. Now, for example, we have a wall and we fix the string between them. It can be like this, or it can be like this, or different other way. Like if this distance is a, now this value will be 0 and this value will be 0, right? So in that way, the wavelength that it can sustain, it will be either lambda by 2 or 2 lambda by 2, basically multiple of only lambda by 2 or 3 lambda by 2, similarly like this one, right? This will be the typical value of A. What does it actually has that does to the equal lambda, right? Right. And before going further, uh, from uh, from de Broglie principle, we know momentum is can be of a particle that will define described as Planck constant upon lambda, right? Or we can say lambda upon 2 pi or 2 pi upon lambda. The same thing, right? So this is basically h bar, and this we describe as wave vector k. Is called 2 pi upon lambda. It will be h bar k. This is basically p. And we also know that p is mv, mass into volume, velocity, mass into velocity. And energy is defined as 1 by 2 mv square, right? Or we can write as p square by 2m, or if you put this value here, we have energy which is h square by k square by 2m. This string was free. It was so it can sustain any wavelength. So it can also sustain any energy. Now, what we have when we confined it or when we put the restriction, be that these two end will be 0. So the value that it can take is like only the multiple of lambda by 2. So it not all value are allowed. Only for the typical value of n, they are allowed. So from here we have lambda equal to 2a by n, and we know a equal to 2 pi by lambda. So it will be 2 pi upon 2 into n So it will n pi by a, right? This is the value of a. And we already have described equal to x square k square by 2m. So it will be r square n square pi square on 2m a square. Now what does that mean is, now since earlier it can take any value, now there are only any specific value of n can be 1, 2, 3. So they are quantized. So energy is also quantized. It will not be. It is not. It will not be like that. It can take any values. Right now, what does that mean? What does that mean? Like if you plot only this, let's say this is energy, and let's say this is any quantized, so the k will be different. So not all value will be there, and it basically parabola equal to x square. So they should have space something like this. This is typical shape of parabola. This is for the condition when it can take any value. So it's a continuous curve. Now what's happened? It can take only very specific value of k, which is like pi by a, right? Or 2 pi by a. In this direction would be minus pi a minus 2 pi a. So only these values are there. So corresponding to this value, only this energy level it can have. So which means now energy is discrete. Now it is not continuous, right? Now I also mentioned earlier, this was the sample size L. The A is very small. Like for example, maybe let's say the distance between two ions very small. So which means if A is very small, well, this distance will be large. Now, for example, the same quantization happen because between the samples, like it also has a boundary. It has also the length of L. Now L is very big. So what does that mean? In that case, K will be N pi by L. So energy will be, again E will be x square n square pi square upon 2n n square, right? Right. Now since L is very big, very large, so which means if and if L is very big, it means this this spacing will be very small, right? They will be very close, right? So let's close this here up here. Since L is very large, let's say this is pi by L, right? Now what will happen? This 2 pi by L, since L be very large, it will also be very near, right? So for this value, for like this position, for 2 pi by L, it again will be very close. So it will be like again very close to this value. So the energy level will be like very close. While in the case where the energy level was very far, in this case the energy level are very close. So it as so that they are continuous, right? So here uh, what we understood from this is that if we confined a particle, or if it is free, it can take any energy. But as we confine the particle movement, its energy become quantized. It cannot take a very value. And as the length of the quantization length increases, they are more closely spaced. Now we will apply this concept to the potential well that we actually previously discussed.